NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey folks, how's everyone doing tonight? Good. Well, thanks for coming out to join us on this kind of rather unseasonably warm October, but we certainly appreciate you coming out. So prior to the Dawn spacecraft's arrival, the dwarf planet Ceres was the largest unexplored world in the inner solar system. Discovered in 1801, it was the first object identified at a time when many were searching for a missing planet between Mars and Jupiter. Initially, Ceres was believed to be this missing planet, but once it was determined that there were many objects forming a belt, Ceres was demoted from planet to minor planet, then to asteroid. Finally, the IAU reclassified Ceres as a dwarf planet in 2006. Regardless of its classification, though, it is an intriguing object thought to have formed within the first few million years of the formation of our solar system, and it straddles the boundary between the rocky bodies of the inner solar system and the ice and water-rich moons of the outer solar system. It may also have a similar astrobiological potential as those icy moons. Having completed its comprehensive investigation of protoplanet Vesta in September of 2012, the Dawn spacecraft traveled to Ceres, reaching it early in 2015 to finally pull back the veil on this mysterious world. Tonight's guest will present highlights from these early science orbits. Tonight's guest joined JPL in 1990, fresh from receiving a PhD in geophysics from Columbia University the prior year. In 2002, she assumed her current role as the Deputy Principal Investigator and Project Scientist on the Dawn Discovery mission to Vesta and Ceres. Her research has followed a long arc from the Earth's ocean floor through Antarctica to Mars and beyond to the asteroid belt. She spent her early career at sea, leading 4 marine geophysical expeditions in the Southern Ocean. But currently, she spends her time studying the fascinating data Dawn collected at Vesta and the new observations at Ceres, while also managing the science team. She has more than 120 publications on Earth tectonics, ice sheet history, magnetic fields on Earth and Mars, mission design for a range of mission types, and the character and evolution of Vesta and Ceres. She has served on numerous committees for NASA, JPL, and other organizations, and has received an Exceptional Achievement Medal and 5 Group Achievement Awards from NASA. Additionally, asteroid 10724 was named, one word, Carol Raymond, to recognize her work on the Dawn mission. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Carol Raymond.
Thank you, Mark, and welcome everybody. I'm so glad to see so many people here. And I just have to mention that that last thing, getting an award, getting a medal from NASA is pretty cool, but getting an asteroid is really cool. So I was really pleased with that. So let's get underway. Just give you a couple of pointers along the way. We're going to take a journey through the asteroid belt, and on my title slide here, you see that in the foreground here is a view of Vesta. Obtained when we were there in 2012, and then this was some artist's rendition of what Ceres might look like. And we'll see that it wasn't quite right. Okay, so the Dawn mission is really a journey in space and back in time to investigate conditions and processes that were occurring when the solar system was forming, literally the dawn of the solar system, which is why the mission is named Dawn. And Dawn's targets are Vesta and Ceres, and these are the 2 most massive objects in the main asteroid belt. So Dawn was selected in 2001 as the 9th mission in the low-cost discovery program. It was a competed program, and they selected the Dawn project under the leadership of Professor Chris Russell at UCLA to be their 9th mission. Now, Dawn is a collaboration of many partners that built, launched, and operate the spacecraft and the instruments. And its rich return is really a result of all the hard work of many, many people within the science team, within the operations team at JPL, and all of our partner institutions. So I just want to give a shout out to these hardworking teams. And in our logo bar, you can see that, of course, we have NASA and JPL and UCLA. The orbital orbital sciences company built the spacecraft. The Italian Space Agency funded one of our instruments, which was built by the International National Astrophysical Institution in Rome. And the German Aerospace Agency funded our cameras, and they were built by the DLR and Max Planck Society. So the contributions that we got from these European partners really helped to make Dawn a very capable mission for a really remarkably low cost. So we are probing deep into the heart of the main asteroid belt to discover the secrets of the early solar system. And let's start at the beginning. So our sun, when it was born, was born from a shock wave, which compressed a cold cloud of gas and dust. And that led to the condensation that formed our star. And that shock is thought to have been related to a nearby supernova explosion. Once the sun formed, this nebula begins to accrete into grains. So it's gas into grains and grains into planetesimals, which are maybe fist-sized bodies. And then the planetesimals grow by merging and then become protoplanets. And eventually you have planetary embryos. And all of these things are merging until finally planets are born. And this whole nebular disk gets cleared out and accreted into these planetary bodies. Now that's the sort of classical and orderly process that we think happened. Now, because of the nearby supernova explosion, at the dawn of the solar system, this nebula was rich in short-lived radioactive elements, aluminum-26 to be exact, and that added a lot of heat in the very beginning, the first few million years. And so anything that was clumping together at that time, these bodies that were forming at that time, incorporated this radioactive material, and so they were very hot. And being very hot, they were able to melt. And when they melted, iron that was in the accreted material could go to the center, and you could boil off a lot of the light elements, the sulfur, the sodium, the calcium, and importantly, the water. So what we're really trying to figure out is what resulted in the diversity of objects that we see today. Is it mainly the result of chemical variations in that nebular disk, and or the time at which the body formed relative to the extra heat or relative to the evolution of that disk? And then after a lot of things formed, what processes mixed all that stuff up so that we had interactions that occurred as it evolved? Okay. So these pertain to some big questions. The answers to these questions pertain to things like how unique is our water-rich planet, and where did it get its water? And then, importantly, where and when in the formation of the solar system were there bodies where the conditions for life were met? Because we do think that life probably formed in many places in the solar system, and then maybe it's still there now, or some evidence is still there, but the only planet we know of, obviously, that has life at the present time is the Earth, and we think that its life is related to water. So we're on a search for water in the solar system, and by looking back in time and finding bodies that were water-rich early on, that gives us a clue to where life may have been existing in the early solar system. So now we're through with our sort of Old Testament. Now we're going to go to a geography lesson. So Vesta and Ceres are located in the main asteroid belt. The main asteroid belt lies between Mars and Jupiter. I'm sorry if this is remedial for many of you. And these two objects really represent original building blocks of terrestrial planets. And as such, they're basically fossils. They didn't get incorporated. They didn't get smashed to smithereens. They exist there as time capsules from this early period. And so by going there and interrogating these witnesses, we can learn a lot about what was going on at that time. So this is what Ceres and Vesta looked like before Dawn got there. These are images from the Hubble Space Telescope. These are the best data available before Dawn. And as you can see, there's some tantalizing bits of information in there, some color variations and interesting concavity at the south pole of Vesta, which you can see right here. But clearly you can't do a whole lot more with these images. Now you may also, and the introduction told you about Ceres as the dwarf planet. So it is one of a family of dwarf planets shown here, which includes Pluto. And interestingly, if you look along the bottom here, you see the distance from the sun in astronomical units. An astronomical unit is the distance between the sun and the Earth. So Ceres is about roughly 3 times the distance between the Earth and the sun out in the asteroid belt. And all these other dwarf planets, including Pluto, out here at almost 40 AU, are way out there in what we call the Kuiper belt. And the Kuiper belt is full of really interesting objects which we're only starting to understand or find and learn about. But Ceres is the only object that's in the inner solar system that is in this class of object, is big enough, and it has the same kind of characteristics. So it is a pretty exciting object just from that standpoint. Now, its peer group also includes icy moons of the outer solar system, and of course, Pluto, the other dwarf planet. And two that I feature here are Enceladus, which is half the size, half the diameter of Ceres, but the moon of Saturn, and then Dione, another moon of Saturn, which is about the same radius as Ceres. And these bodies are very, again, as I said, very icy. We know that Enceladus is active. It has plumes. It's emitting things that have been seen by the Cassini mission. So we're going to be learning about Ceres, as we did about Vesta, by also comparing Ceres to other objects that we know about. Okay, geography's over. Now we're going to history. So this is a really fascinating story, which the Dawn team learned a lot about at our team meeting, which was a couple weeks ago in Palermo, Italy. And Palermo is in Sicily, and it's where the observatory sits, where Ceres was discovered in 1801. And what happened is that back at that time, there was a recognition, as the planets were being discovered, that there was a mathematical progression, as you can see here. This is the distance from the sun in AU. And then they noticed that you could add this factor to Mercury's distance, and you'd find this mathematical progression of twice the last factor and so forth. And this all made sense, except that there was something missing. The plus 24 was missing. And then Uranus was discovered, and it followed the same rule. I think that's going to come next. Okay, and this rule was first identified by Titius, but then it was published by Bode. And so this is one of the first examples of one scientist taking credit for the work of another, and we know that never happens. So it's now generally called the Titius-Bode law, even though nobody can find any significance to the mathematical progression. It was just maybe coincidental, who knows. So anyway, these guys were off looking for a missing planet. There was actually kind of a international survey that was organized, and they called themselves the Celestial Police. And here's this guy, Piazzi, who started working with the observatory in Palermo. He was a mathematician. He wasn't even an astronomer. And he just did a lot of the right things, and he ended up finding Ceres. And then shortly, he was in close contact with Olbers in Germany, and Olbers found Vesta. Olbers actually rediscovered Ceres when Piazzi lost it, because it's very hard, even when you find an object that is something like an asteroid, a minor planet. Then you lose it, and you have to find it coming back around again, and it can be very easy to lose. So it was a combination of mathematics, and Gauss figured out how to calculate Ceres' orbit from the observations that had been taken, and then finally it was rediscovered. So this was really a big deal. And this is a lithograph that hangs in the observatory, and it shows this beautiful astronomical instrument, which is the actual telescope that Piazzi used to find Ceres. And it was revolutionary at the time because it could move in azimuth and in latitude. And so it was called the Circle. And it also had some of the best glass around. And so it was revered in all of Europe for its being one of the best instruments. And here it was in Palermo, and he took very, very careful data, and he found Ceres. So this is Ceres, the goddess of agriculture. And here on her head is the shining star, which is our Ceres. So, and then you see the angels here around the telescope. So it's all very, very poetic. Okay, so about 200 years after that, exactly 200 years after Vesta was discovered, Dawn launched. And if you stop to think about that, that's pretty remarkable. We just knew that there were some minor planets in this vast region between Mars and Jupiter, and eventually they became part of a large collection, which we now call the asteroid belt. But here we are, heading off to go take a look at them, knowing that these are very important objects. And we launched at dawn, which was kind of another very poetic thing. So off we go. It was there was many, many problems with the launch. It was on, it was off. There were rainstorms. There were boats that broke down. The rocket broke down. So many things broke down, but we finally got off. And then one of the things that's really unique about Dawn is its ion engines. And so we use these ion engines to allow us to get to not one, but two destinations in the solar system. This is a first. Dawn is the first mission to go into orbit around an asteroid, around a protoplanet, an object in the main belt. And then it's the first to leave one object and go to another one. So, and this is all, again, in a low-cost mission. So this is really a remarkable feat, and it's all enabled by ion propulsion, a really revolutionary form of propulsion. So we'll see a little bit more about Dawn's journey in a couple slides, but I wanted to highlight the instruments. This is the German framing camera. One thing you'll notice is they all look pretty complicated. They are pretty complicated, and they're very well built, and they're still working today, 10 years after they were delivered to the project. So we have cameras that take images in clear and color filters. We have a gamma ray neutron detector, which is looking at the elements on the surface based on the gamma ray emissions and the neutrons that are coming from the surface. And then the visible and infrared mapping spectrometer is looking at the reflected spectrum of light and the thermal emission, which are telling us about the minerals and the composition of the surface. So what we did, we launched in 2007. We went around the Earth. We passed by Mars and got a gravity assist, and then kept pushing out until we got to Vesta in 2011. We stayed for 14 months, and then we turned on the engines, and we pushed out to Ceres. We got to Ceres in March of 2015, and we'll be here until forever. Once we get into our low altitude orbit, when we run out of fuel, the spacecraft will no longer keep its attitude, so we can't talk to it. It won't have power, but it won't leave the orbit that it's in. So it's going to become a natural satellite of Ceres. And here you can see it in motion. You're going to see the spacecraft leave the Earth. It's thrusting, it's going out to Mars, catches up with Mars, turns its engine off, falls into Mars, gets a gravity assist, helps us to change the plane of the orbit so that we can climb up and meet Vesta at its modestly inclined orbit of 7 degrees. So we get out there, we catch up with Vesta, match its orbit, and then we begin our observations, and we go for about a fourth of a Vestan year, taking observations, and then fire back up. And you see how close Vesta and Ceres are relative to each other in the ecliptic plane here. And that is the reason we could do this dual asteroid mission. So now here we are at Ceres, and you can see Ceres is even a little more inclined than Vesta. So this is really quite a feat for a little spacecraft like this. So at each of these bodies, we're getting a lot of scientific data. We're getting color images. We're making a topographic map by looking from all different directions at the surface. we're mapping the elements. So what, the hydrogen, the nitrogen, sorry, not the nitrogen, the hydrogen, the magnesium, the iron, all of the things that make up the minerals and this variation on the surface. And then we're measuring the gravity field so we can understand better what's inside of the objects. And also we're searching around them to see if they have any moons, which would tell us something about their history. So the two objects, even though they reside pretty close together in the main belt, and they've probably formed within 1 million or so years of each other, are really different. Reminds me of that TV show where there was the two, yeah, okay. But Vesta is very rocky and dry and bright. It's it's the brightest object in the main asteroid belt. So you can actually see it with your naked eye at certain times of its orbit. It has an iron core. Dawn confirmed it has an iron core. It has a mantle and a crust similar to the Earth. The crust is like the ocean crust on the Earth, it's basalt. Whereas Ceres is icy, wet, and dark. And so we expect that inside its core is not iron, but it's rocky, and it's got a mantle full of ice and other rock-type material, and then it has kind of a dusty clay surface, which makes it very dark. So again, why are these two things so different? Was it the chemical gradients? Did they form somewhere else and only achieve their current position based on forces? Was it the formation time? We're trying to get at those questions so we can better understand the whole context in which they were forming. So speaking of context, this is a really nice comparison of all of the asteroids that have been visited by spacecraft by NASA and ESA. The largest one, besides Vesta and Ceres, is Lutetia, which was flown by the Rosetta spacecraft. It's about 100 kilometers. But as you can see, a lot of them compared to our Vesta are rather small. In fact, you can't even see some of them. So we like to say Vesta is not an asteroid. It is a protoplanet. It is, really a different thing than asteroids, which generally are kind of dark and homogeneous and made of fragments, probably, of bigger bodies that got disrupted. But Vesta is an intact body. So it formed, it evolved, and it's still generally in the same condition it was when it formed. And so that's what gives us a chance to really look at what was going on when it formed. Okay, and then Ceres. I think you'll agree with me. Ceres is different, but in the lexicon of our planetary science, these were all lumped together as asteroids for many, many years. And asteroid, by the way, if you know Latin, just means star-like. So at the time they were discovered, they were just pinpoints of light moving in the sky, and so to the astronomers, they look like stars. They were just different. So, but here we have our dwarf planet Ceres, which is obviously a whole different class of objects, as I've already mentioned when I made the comparisons to icy moons and dwarf planets. Okay, so now let's see more about Ceres. What did Dawn find there? So Ceres is named after the Roman goddess of agriculture. I've already mentioned that. It is the largest, most massive body in the main belt. It's almost 1,000 kilometers in diameter, so roughly 600 miles, and only dwarf planet in the inner solar system. So if you've been listening, you know this already. And this is what we think is going on inside of Ceres. The very core of Ceres, because Ceres is large, there's some gravity, there's compression, and that can cause dehydration. So we think that right in the center of Ceres we have something that's a more dehydrated, dry silicate, and maybe even some metal enrichment, but not an iron core. And then surrounding that we have a layer of hydrated silicates. So what are those? That's like clay. Basically, when you add water to rocky material, you get things like clay or mud. So that's kind of what we think is forming the bulk of Ceres. And we do know from its shape and its gravity that it has some condensation in the center and that it has a lot of water still available. And if you go through a model where you say, okay, it's formed to this temperature, the heat had to get out, it would have melted, it would have released a lot of water from the silicates. You would have had a layer of liquid water, a subsurface ocean, during some portion of Ceres history. Not today, because it's now too cold, and so all of that ocean would have frozen out and into this ice layer at the surface. And so what we think is we've got this ice which is really mixed in with rock, and of course there's salt because our ocean has salt. Ceres ocean would have had salt. And then covered by this dusty layer of stuff that's fallen in or been mixed up. And that ice, any ice at the surface would sublimate away. It would just turn into vapor and leave. And so you get this dry, dusty layer at the surface. Okay, so this is kind of what we think Ceres looked like. And why is it important, then, that we have this frozen ocean, or that we had a subsurface ocean in the past? I'll tell you the answer because it's not on the next slide. What we're really curious about is what were the processes going on at that ocean floor? So we had, think about it, you know about hydrothermal vents on the ocean floor of the Earth. We know Enceladus has some sort of hydrothermal systems at the boundary between its rocky core and its ocean. And that's where the environment for life is most conducive. And so we're really interested to know more about what that environment was like in the past. So what are we looking for? Of course, we're not going down there. We're not sampling anything under the subsurface. But we're looking for what's on the surface, the telltale signs of what was happening, because that stuff came up and it got left on the surface as deposits. So we're looking for what minerals are on the surface. Are there salts? Is there organic rich material? And the clays that we expect make up most of the interior. And then is there other material that was brought in by impactors? And then we're trying to figure out how much water is being released over time or sublimating from the surface, and identifying whatever the energy source for that is. We want to know more about that ice shell composition, because that tells us more about the evolution of the body as a whole. And we do that by looking at the crater shapes. And I'll expound a little bit on that coming up. And then finally, what I was just talking about is this exchange of material and energy, and how much the environment would be supportive of some biological activity. Now, we can get a little bit at the interior structure with the gravity, and that's to map the density of the body as a whole and the shape of that rocky core. So here is a comparison at scale of Europa, Ceres, and Enceladus, Europa being the moon of Jupiter, which is now the target for one of NASA's upcoming missions. And we're going to Europa because we think, we know it likely has a subsurface ocean, and we think it's probably one of the highest potential environments for life outside of the Earth in our solar system. And if you compare Europa and little Enceladus, which has these plumes shooting out of its ice shell in the south because of cracks, and then we also know that there's some hydrothermal activity going on there in the subsurface ocean. Well, here's Ceres, and it's sitting right in family with these two objects. The only difference being that these guys have a lot of tidal heat. They're orbiting these giant planets, and the tidal forces cause a lot of friction, and that friction melts the interior. And so at the present day, Europa and Enceladus have liquid oceans. Ceres did in the past, but mainly because it was so much closer to the sun that it had a lot of solar energy that would keep it warm. And so for some billions of years in its past, it likely had liquid water. So these three objects all had the essential ingredients: the liquid water, the chemical ingredients, and an energy source. And so that's why we're really interested in learning more about what Ceres was like back then in a more definitive sense. Okay, so now this is a really cool movie, which is showing you the spacecraft with its blue ion beam traveling to Ceres. approaching Ceres, and then there'll be a series of images showing you as we get there what Ceres looked like. So you can imagine everybody's excited. We're getting there. The couple of pixels, and now it's better than Hubble resolution at this point. And everybody's really excited now. And it starts to grow in our view, and we start to see surface features, and all kinds of strange things start to appear. Everybody's getting really excited. And then we got our first rotation movie. These were all optical navigation images. And then we saw it in all its glory in a full rotation, and found those incredibly bright spots, which are still puzzling the team to this day. And then this is just a quick animation showing how Dawn got into orbit around Ceres. And this is kind of a fun story because the spacecraft safed back here. It shut itself down. And so it wasn't on its regular planned trajectory to go into orbit. It went screaming past Ceres too fast, and it was going to this giant elliptical orbit. So the team figured out how to basically make a U-turn, come back, and put on the brakes, and get into that same orbit that we wanted. And they did this in a matter of weeks, and it's a huge mathematical problem to solve. So that was another, it was like, they rescued the mission. It was really impressive. So another thing while this continues is I just want to mention how wonderful it is to work with such incredibly smart and creative people, because this is not like rote stuff. This is, really first-time activities almost all the time. So then we got a little closer up, and this is what we found. This is now the surface of Ceres unwrapped, and you can see those bright spots in the crater here, but you also see there's other areas that are quite bright as well, and this whole region here, which you could see from the Hubble as well, is a little bit brighter. But overall, the surface of Ceres is very dark. And there was craters everywhere, and that was a little puzzling because of expecting that ice at the surface. If you have pure water ice, it basically doesn't have strength. It's very easy to deform, and so if you have an impact into the ice, it basically will flow back and fill in the crater. And then after so much time, you won't have a crater anymore. But clearly, there are craters. So clearly, there wasn't a layer of pure water ice. So this is how the crater shapes and distribution is telling us about what that ice shell is made of. And then we had some areas that are rather smooth, like here, and some areas which I'll be focusing on a little later, particularly over here, which were quite rougher and has some fairly chaotically fractured terrains. So the bright spots. These spots, as far as we can tell, are unique in the solar system. We don't see anything nearly this bright or focused into small deposits. So, the going in thoughts were ice, salt, some combination, ice being the most reflective material that you could have, salt being highly reflective, but not as reflective as ice. So now what we know is that it doesn't require ice because the spots are not as reflective as ice would be if it was in its pure form. So it's consistent with salt. We don't expect, as I said before, the ice to be stable at the surface. It would be basically sublimating into space very rapidly. So salt is a good going in hypothesis, but many people would like to see an alien civilization as well. So we're keeping our eye out for that. The brightness of the spots indicates a recent exposure or a process which has brought material to the surface recently because, as you may know, anything that's exposed to solar wind, to the radiation of space, will usually darken over time. So we're wondering if they could be related to water vapor emission that was detected by the Herschel Space Observatory in the vicinity of Ceres. And this was a few years ago when Ceres was going through its perihelion, so passing closest to the sun in its orbit. And they detected by a very sensitive spectrometer that there was water vapor in near Ceres environment. So this kind of adds to the whole mystery of what is going on at Ceres. Okay, now a couple of looks at the whole surface once we got resolved data. Again, you can see the brightness variations, that smooth cratered basin. Here's a very smooth area. There is a lot of fracturing going on here, and you see the fractures going through there. The bright spot crater, another bright crater called Dantu, I'll show later, and this one called Hylani. So this is showing you in grayscale the shape and brightness. And then if we color the topography, you can see better now the crater outlines. And you can see that we've got kind of a broad high area here, a lower area, which is part of that smooth terrain, and then another high area. So a lot of topography, a lot of brightness variations, a lot of morphological variability, and in these rough, smooth terrains, which don't necessarily relate to the differences in the topography. So lots of stuff that we can use to try to understand what's going on at Ceres. But the good news is it's not immediately obvious. So it gives us something to puzzle over for a while. And then just recently, this was actually publicized last week, we got a whole batch of new names for features on the surface. Our naming theme is agricultural deities, because Ceres is the goddess of agriculture. And we've collected names of agricultural deities and festivals from around the world. So this is one of the bodies where instead of it being all Roman mythology or a lot of sort of more European centric names, we have some really interesting names from all over the world. And the couple of places that I'll be showing you close up are Occator Crater, which is the bright spot crater, Dantu, which is in the smooth, low area, Kirwan, which is a very shallow kind of basin with very little definition, and then Hylani over here. Okay. I'm not sure why that slide's not showing up, but that's okay, because I can go over here and show you. Yeah, so Kirwan, I'm going to give you some close-up, and these two craters over here, Urvara and Yolode. And so you notice Urvara is quite deep, and Yolode is not, but it has a deep part in the middle. And Kirwan also has that kind of structure with a deep center and then kind of a shallow basin. So we're going to have to go past that. Okay, so here's Kirwan close up. This is the outline of it, and you see it's got kind of some variations in the topography within it, which give you the impression that stuff is sort of rising under it. The crater rim is not very well defined, and it's not very sharp. It has kind of a scallopy texture. And it is located in this region of smoother topography. So we're thinking this may be one of the examples of a crater that occurred in an area that was more ice-rich or warmer, and so the material was able to flow in response to the impact event. So this may be because it formed very early when Ceres was a little warmer. Could be that there was just more ice in this region. And so we're doing modeling right now. We're trying to get to the bottom of what causes the different types of crater shapes and morphologies that we're seeing. So here's Urvara and Yolode. Remember, Yolode had the deep center and then the shallow basin, and Urvara was quite deep. And you see Urvara has this nice central peak that's well defined and is much rougher than Yolode, and you'll see that in the next one. So here's just a close-up of Urvara, and all of these fractures are coming out of Urvara. There's terraces along the side, and then there's this very rough terrain to the south. And then you notice that right in the center of the crater is very smooth, and we're thinking that these are some sort of low viscous melts. Something is flowing in the bottom of these craters. And the team is trying to figure out exactly what that is and when it happens. Does it happen during the impact or by some other process? But one thing that we've concluded by looking at this is that the strength of the crust over the body is quite heterogeneous, meaning it's varying, and it seems to be stronger in some places than others. And here's a beautiful picture that we got early on. This is called the Terminator, when you see the light to dark transition. Gives you a lot of definition of topography because of the shadows. And here you can see Eulode and all those terraces and these fractures. And then here's that, this is Urvara, and here's that Eulode basin. And you can see that, again, that smoothness and the more diffuse topography. And so these are two things sitting right next to each other that seem to have very, very different properties that we have to tease out what's going on here. And then here's an interesting comparison of craters on Vesta here at the same scale, a 40-kilometer crater on Vesta, a 48-kilometer crater on Ceres, and a 49-kilometer crater on Rhea, one of the moons of Saturn. So Vesta is a generally bowl-shaped, simple crater morphology, and at the same size on Ceres, it's looking much more scalloped, and the rim is not very well defined. You have a shallower bowl, and then you have this smooth floor. Now, the difference at Rhea, you get the same sort of rim or morphology, but you never see the smooth floors. And so Rhea is a lot colder than Ceres. And so this is a good indication or example of how Ceres is really straddling the boundary between these dry, rocky bodies of the inner solar system and these icy moons of the outer solar system. These are very cold. Vesta and Ceres have about the same temperature, but clearly whatever the material is on Ceres is very different than Vesta. So we're investigating this, and by doing these comparisons, we're learning a lot more about how these bodies are responding to forces and stresses, and eventually how does that affect the way the material is convecting in the interior and mixing. Now, this is another result that was publicized last week. It is our first color map of Ceres from the framing camera data. And it looks technicolor, and wow, it's all bright and exciting. But the color variations are really small. So this is just enhancing them. But the difference in the color, if you looked at it with your eye, would look pretty gray. But what we're doing here is trying to accentuate what differences there are. And one thing that should pop out at you is some of these areas where the crust is very bright, Hylani, Occator, and here is Dantu. You see it's also quite blue, which means that the spectrum, so from red to blue, from short to long wavelength, usually bodies have a spectrum which gets higher as you go towards infrared wavelengths. The reflectance is higher. But when you have a bluer spectrum, it's flatter, so it's reflecting as much blue light as there is red, and that usually means a fresher surface. It's a different mineralogy. So the upshot here is there's something special about these areas, which are also showing us these very bright deposits. And then we have a couple of movies of two of these craters. This is Dantu. This is the one that's in the middle of the very large, brighter area. And this is so interesting because you can see that the bright material in here is very discrete deposits, but it's also distributed all over the crater. And it's popping out in the crater walls, and it's just sort of coming out diffusely also in the ejecta. And you also notice that the crater wall here looks a lot different than you might be familiar with from other bodies like the moon. It's got sort of, almost looks like flour, the very steep walls, and you can see things that have slumped down into the crater. And then our favorite Occator Crater with our brightest material, and again, has that really sharp rim over here, a lot of slumping coming through on this side, and just a really strange morphology in here of some lumpy material and some smooth material, and then these very, very bright areas. So now we'll see what happened when we got closer up. And this is our latest beauty shot of the Occator Crater. So again, I was showing you these kind of slumpy deposits. And now you can see that those two bright lights that we saw as we were approaching Ceres have resolved into a whole complex of deposits. This is the source of the very brightest material. It's a depression. It seems to have fractures radiating away from it. And you can see there's also dark material associated with that brightest material. And then there are some fractures that go through here. And this other area where you have a collection of the bright spots, as you can see as well as I can, there's some very discrete point-like deposits. So whatever this is, it seems to be related to a pit in the middle of the crater. And there seems to also be related to the fractures. So that's about as far as we've gotten. You can also see the very smooth area over here. And as I said before, because we don't expect ice to be stable on the surface, it would be very surprising if there was a lot of ice in these deposits. Okay, another really cool feature that we found was dubbed the pyramid, and you may have seen it in some press releases, because it's basically just this thing sticking up out of the surface. And there aren't like a lot of mountain ranges on Ceres, but there is this lonely mountain in the middle of basically nowhere, and it has this really intriguing streaky layering. So it got a name last week, and it's now called Ahuna Mons, which I think is a really cool name. So let's take a closer look at that. So now you're looking down on it, and you can see that the top of it looks a lot like the surrounding terrain. It has this sharp boundary, like it is literally sitting on top of the surface. It's not, you don't get the feeling like there's these slopes that kind of come up. It's just plopped down there on the surface, apparently, and then you've got these streaks of bright and dark material coming down the side. So the team is busy trying to puzzle out how that thing got there. Okay, so you've made it this far. Now, it's a little movie and some nice music. And you can get up and stretch if you want, because we're going to take a look at Vesta after this, and then I'm going to wrap it up. But this movie was made from our highest orbit data, so it's not that high resolution, but it's still a nice overview, by our colleagues in Germany at the DLR. And the guy that makes the movies, he also writes the music. He composes this original score for the movie. So again, it's really fun to work with these creative people. And you can really get a sense of how bumpy Ceres is by looking at this movie. It's just very lumpy. It does have some vertical exaggeration, but it is really lumpy. Okay, so let's give him the credit that is due, as Stefan Elgner writes the music. Okay, so what about Vesta? We didn't forget about her. She was our darling for 14 months, and she's named after the Roman goddess of the hearth and home, which is appropriate since she was basically melted in the fire, and is the second most massive body. Now, Pallas and Vesta are very similar in size, but Vesta is more massive. Okay, so this is Vesta coated in her coat of many colors. Again, the color data from the framing camera enhanced in false color to show you variations on the surface. In the case of Vesta, these colors are much more pronounced, is much richer in color diversity, and as I said, it is much brighter as well. Look at this orange deposit here. the green is showing you where there's a certain type of lithology that we know of from meteorites from Vesta. And this purple-blue is another kind of more basaltic type of lithology that we also know from the meteorites. So what you get from looking at this is that, yeah, there are some general areas which are more like basalt or eucrite, and there's some general areas which are more like diagonite. But then you've got a lot of mixing and a lot of kind of exotic deposits around on the surface. So we had a lot of fun picking all that apart. And one of the reasons that we went to Vesta is that we have all these meteorites from Vesta. There are more meteorites from Vesta than from the Moon and Mars combined. And they've been under study in labs for decades. So we knew they were from Vesta because the reflected light spectrum of these matches telescopic spectra from Vesta. And when we got there with Dawn, we were able to confirm that it was the source of this class of meteorites, the HEDs, the Howardite Eucrite diagonites. So the Dawn at Vesta became kind of a reverse sample return mission. And we did learn a tremendous amount by having those samples and then having the data of the parent body from which they came. So we knew from Hubble, I showed you that early on, that there was a concavity in the south. What we found was not only was there a giant impact basin, you're looking at it on edge down here, but there was a second impact basin underneath that was almost as big. So Vesta got hit, it was a 1-2 punch, and this is the equator of Vesta. So this thing is huge compared to the planetary radius, and it's a wonder that it didn't shatter the whole body. And so this is the largest crater relative to the body size in the solar system, and you can read this. It would stretch from Washington, D.C. over the North Pole to Tokyo on the Earth. So pretty cool stuff. Topography of Vesta is very rugged. The lowest point here, 14 miles, the highest point, 12 miles, and it all occurs in that impact basin. So here's the lowest point, and then the highest point is over here on the crater rim. Here you can see this is the Rhea Silvia basin. Here's the older Venonea basin, much more subdued. And then you've got this giant mountain in the middle of the Rhea Silvia basin. Not unusual for large impact craters to have an uplift in the center because of the movement of material that is being moved out of the way and it rebounds up. But this is much higher than you would expect even from that process. And so it is, if I can stop the movie, it is the highest mountain relative to the body radius in the solar system, or it rivals Olympus Mons for being the highest, and twice as high as Mount Everest on the Earth. So this is a pretty interesting body. And those impacts left these scars around the equator of Vesta, so basically global tectonic features from the shock that went through during those impacts. So Vesta has really experienced a lot of geology and a lot of mixing processes from impacts. This is a wonderful example of this light and dark material. We found lots of dark material on the surface and some really, really bright material. So here you see it layered together as a result of a small impact. And when you look at that in the reflected light spectrum that gives us mineralogy, you see that there is like a compositional boundary going right through the center of this. So a lot of mixing and exotic materials showing up on the surface of Vesta. And one of the things we wondered about was what that dark material was. Now, a big surprise after finding all this dark material and bright material was the gamma-ray neutron detector found that there was elevated hydrogen on Vesta. So because Vesta melted, boiled off its water, we thought it would be bone dry. It should be drier than the moon because the solar wind can't really get the hydrogen out there as efficiently. But what we found was hydrogen levels which are like 4 times what would be expected. So there was something else going on, and this is the big hydrogen anomaly, and you see it's localized too. It's not like the whole surface is elevated. Clearly, the big impacts dehydrated the surface, and that's why you see almost no hydrogen down here in the south. So after noticing that the hydrogen anomaly coincided with a preponderance of dark material, we turned to the meteorites. said, what could this be? And everybody was focusing on these mineral clasts. I'm going to study, what is that and what is that? And they would just ignore these dark things. It's like, oh yeah, that's a carbonaceous chondritic clast. Well, a carbonaceous chondritic clast is a piece of material that's associated with a primitive body from somewhere else in the solar system that's much more water rich. And here it is, mixed in with the other materials on the surface of Vesta. So it was like, aha, that's what we're seeing. But we then came to realize that this is a large percentage of that near surface material. It's showing up in the data from our neutron detector. So clearly this carbonaceous material was coming to the surface of Vesta, being mixed in, and bringing the water which was bound in those minerals. So there was a couple of other really interesting features that we saw on the surface of Vesta. And this Occator Crater is kind of like a poster child for some of these things. So you'll see close up, but basically there's light and dark material, there's this irregular shape, there's a pond in the bottom of smooth material with pits. So we took a look at that, and here we're going to just fly around it a little bit. And you see that there's kind of a more rocky looking wall over here. And then as we come around this side, you see this smooth bench, very smooth material, kind of seems to have flowed down into the bottom of the crater where we had the little pond and some pits, which we'll see close up in a moment. And in general, as we come around, then you'll see that very bright layer showing up over here. So here's another look at that bright and dark material. So here's the dark material, the water-rich material, and it's under the bright material. It's also showing up as like discrete layers. So clearly this is not just a couple of impactors. It's been an important process in Vesta's evolution that this dark material has been delivered to the surface. And what we're thinking is that these pits, and here you're seeing them close up, they may not look like pits to you, but they are. Sometimes your eye fools you and they look like they're coming out. And what this is what's left behind when bubbles of gas are exiting the surface. So if you've been to Yellowstone and seen the bubbling mud pits, it's kind of a similar process, at least we think. And there's certainly this central structure, and then you get the pits all around it. And they also show up in one other very young crater, and that's this Cornelia. They're down here in the bottom. We see this is all dark material, and this is bright material that's slid over. So we think that the slide goes down, covers over the dark material that's still processing impact heat. The water is being released from those water-rich minerals, and then the gases are escaping. And here you can see the dark material in this false color image, and you can see the pits on Marcia versus some pits that we see on Mars. And so by analogy to Mars, where they're attributed to water to escape a vapor from the crater floor, we make a much firmer connection. So we think that since water is the most abundant liquid in the solar system, that this water is being liberated from this dark carbonaceous material, and there may actually be ice in the subsurface as well. So the last piece of evidence about water on Vesta was so-called gullies. And this is an example of a network of gullies in the Cornelia crater. And you see that they're kind of dendritic, like they look like a river drainage pattern, versus these gullies in another crater, which are all straight and are associated with dry granular flow. And you see ones like this on the moon. So these sinuous intersecting gullies have been interpreted to have been caused by flowing water. And now, like saying we think water flowed on the surface of Vesta is a pretty heretical thing to say, but all this evidence is really pointing towards a very ephemeral transient water flow. And so a model that was published earlier this year shows maybe an ice-rich body came and impacted Vesta, and some of that ice was sequestered in the subsurface. If you cover it over with ejecta very quickly, it can basically insulate the surface from the evaporation or the sublimation. And then you've got an ice layer in the subsurface. Then you have another impact comes in with impact heat, and it warms it up, releases the water either from an ice layer or from a layer of material which has bound water in the minerals. And then that water is released down the sides of the crater and forms this pitted terrain in the bottom. So this is a model that attempted to explain all these observations that we're seeing, but it's still quite controversial. So I'll leave you with these questions. We're still grappling with, is there buried ice on Vesta? Are all these water type features coming from minerals that are releasing water, or could there be ice lenses in the subsurface? That's a very important question for solar system science. And then, if so, where did it come from? And then, did it come from possibly water-rich impactors like Ceres? Is this an object like Ceres? And did Ceres-type bodies also deliver water to the Earth? We think that wet asteroids are probably the most likely way to deliver water to the Earth now that we've gotten an answer from Rosetta, from comet Churyumov-Gerasimenko, that its water doesn't have the right isotopic composition to match the Earth's water. So comets are now a little more out of favor than they were before, and now we're turning to wet asteroids as the most likely source to bring water to the Earth. So I'll just end with a summary here. Dawn's exploration of Vesta and Ceres is testing long-held paradigms and shaping new theories. We're still way in the middle of all of this work, but it's already having some profound implications. We know that protoplanets were forming very early during this hot phase of the solar nebula, that they delivered their iron cores and this rocky material to the forming terrestrial planets. The scattering of material between different parts of the solar system was leading to mixing and diversity, and that was both in the distribution of material making up the planets, as well as the asteroid population of sort of leftovers. Comets and wet asteroids delivered water to the inner solar system, as shown by the hydrated material on Vesta, and that these wet, icy bodies like Ceres had geologic processes, and they may have been environments conducive to life. So for all of these reasons, we're very pleased that we decided to go to these bodies. We're extremely pleased that everything worked out so well and we got such great data sets. And I'm also very happy I could share that with you tonight. Thank you for your attention. Now I'm going to find something fun for a backdrop. Let's leave that one. Okay, are there, if you want to ask a question, can you please use the microphone?
That image of Canalea looked like it had a flow feature in it that looked more like fluid flow than dust flowing. Was it actually a strangely shaped fracture?
I'm sorry,
In the Canalea crater.
Cornelia or?
Canalea.
Canalea. Oh, Canalea, yeah, I know what you're talking about. Yeah, it's likely it was some sort of a mass wasting slumping event. And it was caused by the little crater at the side overturning the surface and the ejecta falling into the neighboring crater. But the really interesting thing that I'm sure you saw is how the layering was maintained as that slump was going in there.
Without comet-like jets or Enceladus plumes, how good will the deuterium-hydrogen information we'll get be on Ceres from the gamma rays and the neutrons? Will we be able to constrain that?
No, we can't, unfortunately. So we have to go back.
Thank you for your presentation. I have a two-part question. Number one, I understand the mission was propelled by ion propulsion and hydrocortisone. Is this going to be the case in future missions? And number two, regarding the bright spots in the crater, I understand that it could be salt or it could be reflective materials, and I was wondering if the spectrometer found anything above and beyond this.
Yeah, okay, so first question, ion propulsion is an extremely efficient way to explore certain parts of the solar system. The asteroid belt is really a sweet spot. For a place like Mars, it's, chemical propulsion is probably just fine. But to get out to a lot of these objects, you have to use ion propulsion. You just can't do it any other way. So the answer is yes. There's going to be many more now that we've done this successfully, and we're likely going to be able to get to some really interesting destinations. So your second question, the $64,000 question, remember when $64,000 seemed like a lot? Is yes, the spectrometer can tease out what these specific minerals are, but it's contingent on a few things. One is they have to have the resolution, and the data set that we've just are completing now likely has a resolution, but it hasn't been fully processed. And then the other thing is some of these materials, because they're mixed, salts, organics, water, hydration bands, is very, very complex to understand spectrally. So you have to do modeling where you combine all these different things together in the right proportions to match your spectra. And that's a very time-consuming process. So we will have definitive answers, but it's going to take a little bit of time.
Thank you.
You're welcome.
I'd just like to make two observations. This image, to me, looks like maybe a comet impact that broke up before it hit the surface, and you got a whole bunch of fragments that splashed down in a similar area. And a comment on the Vesta, those gullies and streaks that you saw on the side of the craters, they're reminiscent of the RSLs that were found on Mars,
They
possibly
are.
possibly flowing water.
Yeah, it was interesting to me because we have had discussions about the similarities with the RSLs, and there's been a lot of debate about those on Mars, whether they're CO2 flow or water flow. So this announcement last week that you had evidence for water coming out of the minerals and actually flowing was considered to be a huge finding, but I guess this is too indirect because we're not. It's not quite catching on to the extent that the Mars finding did. But I do think that again things are really moving forward so quickly now in planetary science because we have these very detailed data sets. We have time evolution, and we can compare bodies across a wide spectrum. So it's a very exciting time.
Hiya. The plumes detected on Ceres as it was passing through perihelion is caused by sublimation of water?
Well, that
Or-
yeah, we would assume it is.
And then the craters on Vesta, they kind of remind me of like how sand flows. Is it a coarser sand-like material that coats Vesta, or what causes them to look so sand-like?
Yeah. Okay. So back to the Ceres question. What Herschel found was water vapor. So we know that it's water vapor. How it's coming out is the question. Whether it's just some ice that's in the subsurface and it's all sublimating, kind of over the whole surface, because this is still a very small amount of water, or if there's a certain place like that where there's some jet coming out. Well, we don't see a jet. We would have a hard time seeing it, but we have looked very carefully, and we don't see any jets coming out.
Would the so could the top layer of this be like frozen ice, water ice, and then as it passes closer to the sun, the frozen water ice sublimates, and then under it be liquid water ice, and then, or liquid water, not water
Yeah.
ice. Could that flow out as a plume, or could there be
so-
like a cap?
Yeah, it's a good question. It's unlikely that it's ice because it's just the vapor pressure in the vacuum. The water will just disappear to a certain depth. Now, if that ice in the subsurface gets exposed, then for a brief period of time you might have some icy material, but it's going to go away very quickly. So. So it is pretty unlikely that we think. And I just want to go back to the Vesta question for a moment. The regolith on Vesta is an impact gardened, dry, basaltic rich, silicate rich, granular material, and it's very porous. So it is, sand is not a bad analogy, and that's why you get these flows that look like, something you'd see out in the desert, just the big kind of mass wasting slump down the sides of the crater.
Can you hear me? Okay.
Yeah.
My question is, I understand the mission, but I'm kind of curious about Mars. You have a rover on Mars, right? Mm-hmm. Have you tried to put any type of living organisms to see if they can survive on a planet?
Actually, so they're trying to do the opposite, which is make sure we don't send anything to Mars that would confuse the search for life on Mars. If there's life on Mars, then if we bring something with us, then we'll never know what was there. So, you're way too far ahead in your thinking of when, because we're talking about sending humans to Mars, which I think is life. And if we send humans to Mars, then we're no longer going to be looking for life on Mars because we'll just be looking at what humans brought with them.
My question's kind of about the nature of the spacecraft, and it's one of the lower cost missions, and what sorts of unique considerations went into choosing the instrumentation package for this particular spacecraft versus others?
So we had to find the minimum set of instruments that could answer the major questions that we could think of ahead of time, and you never know what you're going to find when you get there. We weren't thinking along the lines of what we found at Ceres, but certainly, cameras and spectrometers are kind of the workhorse of any planetary mission. And the gamma ray neutron detector was critical for looking for water on Ceres, looking at, trying to match the rocks on Vesta to the meteorites. So it gave you another dimension other than the mineral composition that you get from the visible IR spectrometer. And then gravity is kind of for free because if you do the navigation precisely enough, it tells you about the gravity field of the body. So that didn't require any extra equipment. So it was cost constrained and mass constrained, and those three instruments just were the ones that we thought were going to give us the most information for the resources we had. And then, because we could get two of them from our European partners, that made all the difference, because that contribution, those instruments cost between like $20 and $35 million a piece. And so plus all of the people that are working and all the operations over time add up. So it enabled us to do this mission as robustly as we did by having that partnership.
Hi, thank you for your science. Just curious, I think you may have already answered this question, but are you also searching for other elements such as helium-3 on some of these bodies?
We're not going to be able, no, because we can't. Okay, I have a question from online, a couple. Okay, so SIBA 5618 asks, In December, will we get a confirmation of what the bright spots are? So, and the reason I think it's obviously somebody who knows something about the mission, because in December, we'll be just, attaining our lowest altitude orbit. We'll be just 375 kilometers above the surface within one body radius, and that's when our gamma ray neutron detector gets the resolution of the elements on the surface. So we're getting high resolution data and we're getting a new data set. I think by December we will have a pretty firm answer on we'll have a firm answer on what the bright spots are, because as I mentioned before, we'll have processed through the spectrometer data, and we'll have a lot more time to think about the geology that's going on and what process might have emplaced them. Okay, and then Karen NX asks, will you publish multispectral rasters? The data from the mission are all being archived with the planetary data system. And there's a big data delivery going on right now from the initial phases of the mission, and that includes all of the color data, the visible and IR spectra. And so they would be available for anybody who wants to make anything they want with them. And then our Curry asks, what advice do you have for students going into solar system science? Do it. No, seriously, there's really a lot going on right now. And not only do we have a lot of these lower cost missions, we're going to a lot of different targets, and then we're getting much more detailed data sets about the planets. The Europa mission will be a fantastic new view of one of the most interesting objects in our solar system. And if that weren't enough, there's a whole revolution going on with CubeSats and small sats. And once that really is fully realized in the planetary environment, in the interplanetary space, we'll have a ton more data, much more sampling, both spatially and temporally, which will be really important. So I think there's just going to be a huge amount of cool data coming through over the next few decades, as long as NASA and the taxpayers continue to support it. So if you like it, you might tell people that. But yeah, it's going to be a bright future. Any other questions?